Hello everyone, and welcome to a discussion of gravitation inside of the Earth. But before we go inside of the Earth, it's important to remember what we know about gravitation outside of the Earth. Mainly that Isaac Newton, when he was developing his law of universal gravitation, came up with something which we call his shell theorem, right? Which says that a uniform spherical shell of matter attracts something that's outside the shell as if all that matter were concentrated in the middle. And we talked about how this would, of course, require an integral, right? Second semester calculus, because basically you would break the Earth up into a bunch of pieces. Each piece would exert a force of attraction on the apple with a force given by the law of universal gravitation, and then we would need to vectorially sum all of those forces. And of course, if we wanted a better estimate, we would break the Earth up into more pieces and more pieces and more pieces till they became infinitesimally small. We had an infinite number of pieces, the sum of which is an integral. Right? Remember that this was kind of his explanation for how he must have known calculus long before Leibniz, right? Because he would have needed the shell theorem to fully apply his law of universal gravitation. Maybe yes, maybe no. One of the big historical points in physics. But right, this was the shell theorem. Well, there's a corollary to this shell theorem, right, which replaces all those little forces with the one when it's concentrated at the center. Right? This is all about if that spherical shell of matter attracts a particle that's outside of the shell. Well, what if it's inside of a shell of matter? Well, in this case, the shell theorem predicts that the outside shell of mass will exert no net gravitational force on a particle that's inside of that shell. Okay? Again, it's going to take an integral. You can think of it this way. If it was, say, near the top of a shell, the parts nearby, right, would exert a bigger force because of smaller r's, but there's not as much mass nearby. Right? There's more mass further away, which balances everything out and a net force of 0. But be careful here. Just because there's a net force of 0 doesn't mean there's no gravity. Right? Gravity is still pulling a particle inside of a spherical shell of matter in all directions. It's just that the net force is 0. You with me? So if you were inside of a shell, you would still get pulled apart, right, by all of those particles out in the shell. It's just that the net force would be 0. Okay? So let's then consider if we could somehow magically drill a hole through the center of the Earth. What would the motion of something dropped into that hole, what would it look like? Well, let's use the proverbial apple. And let's say it gets to about here, which is where we're going to analyze it for the moment. Of course, there's a force of gravity acting. But according to this new version of Newton's shell theorem, this mass that's outside of the apple exerts no net force, right, on the apple. Only the mass inside of the shell exerts a force. And it exerts a force as if it's acting at the center. Right? Our first version of the shell theorem. So this would be a distance we're going to call r away from the center. We're going to have to assume a uniform density Earth here. So, a big if, because the Earth is not a uniform density. But if we have the density of the Earth would, of course, be the mass per unit volume. And if we're talking about the only part that's going to count here, that's going to exert a net force, is the part inside of the shell. This would be the mass inside divided by the volume inside. By the way, this is the Greek letter rho, which is conventionally used in physics for three-dimensional density. Okay, you could use a capital D, but that's distance or other things, so they tend to use a rho. So, of course, this is a sphere of mass, and a sphere has a volume of 4/3 pi r cubed. And if we solve for the mass inside, we get the mass inside is equal to 4/3 pi r cubed 4/3 pi r cubed times the uniform density, right, of the Earth. Or in this case, we'd use the average density of the Earth. Now, the force of gravity acting on that apple would be equal to big G, the gravitational constant, times the mass of the apple, times only the mass inside the shell, because the mass outside the shell exerts no net force, all over r squared, the distance to the center, right, from center to center, squared. But the mass inside, as we just found, is 4/3 pi r cubed times the uniform density of the Earth, or the average density of the Earth. Notice that the r squared on bottom cancels with 2 of the r's on top. And if I factor that r out, which I can do because it's multiplication and division, so it's commutative and associative, we get 4 pi big G mass of the apple times the density of the Earth times r. But what do you notice about 4 pi big G, the mass of the apple, the density of the Earth, right, and the 3? They're all constants. So just to simplify things a bit, let's call this K. K for constant, all right? Just so that we can kind of get it out of the way and see what's going on, okay? Now, I'm also going to put a sign onto this, right? And that sign is negative, right? Because it's an attractive force, right? The force of gravity is always an attractive force, so we have to put the negative on there, right, to make it attractive. And then look what we get. We get that the force of gravity, which is causing this apple to fall through the Earth, is equal to negative kr, where k is a constant. In other words, the force of gravity is proportional to the opposite of the position. Well, where have we seen that before? What kind of motion do we get where the force is proportional to the opposite of the position? Yeah, that is simple harmonic motion. And so the apple would act like a simple harmonic oscillator with a position r given by our simple harmonic oscillator position function, right? Re cosine of omega t plus phi, where Re is the radius of the Earth. It's the amplitude of the motion, right? The farthest it would go would be at the edges, right? So it's the radius of the Earth is the amplitude. This is the angular frequency. This is the time, right? And this is where it starts from, right? The phase angle. So this is a loaded R, right? But by showing here that we get this simple harmonic motion, right? When we drop it, then it would look like this. And if we could neglect air resistance, again, another big if, right, it would just oscillate from end to end. So maybe we could drop the apple here and somebody standing on the other end, when it comes out the other end and stops, could grab it and pull it off, right? Stop it from oscillating. Now, there are all sorts of things we had to assume here, right? We had to assume the Earth was a sphere, which it's not. It's an elliptical spheroid because it's spinning. It's thicker at the equator, thinner at the poles. Secondly, we had to assume that the Earth was a uniform density, which it is not. The mean density of the Earth is about 5.5 grams per centimeter, or I think it's grams per centimeter cubed, which is in the metal range. Okay, and the surface of the Earth is definitely not in the metal range, which tells us that the center of the Earth is, a molten iron core. So, be hard to drill a hole through the center. But if we could do all these things, right, and the Earth is also, we have to assume, is a uniform density, which it's not. The surface density is actually less than the center density, but, if we could have the perfect planet, we would get simple harmonic motion. And the AP people say you have to be able to prove that and understand that that's what would happen. So I hope you've enjoyed this brief look at gravitation inside of the Earth.